Capacitor problem. An 8.2 nanofarad parallel plate capacitor is connected to a 3-volt power source. A. What is the charge on each plate? B. Calculate how much energy is stored on the capacitor once fully charged. And C. If the distance between the plates were doubled. I. How does the charge on each plate change? I. How much would the stored energy change? What is the charge on each plate? We use our equation for capacitance, which is C is equal to Q over V, charge over voltage. And we want Q, so we multiply both sides by V to solve for Q. So we get Q is equal to CV. We substitute in our givens. Here's the 8.2 times 10 to the minus 9th farads. And here's the 3 volts. Carry out the math. And when you multiply farads by volts, you get coulombs. So our answer is 2.46 times 10 to the minus 8th coulombs. To find the energy, we use 1/2 CV squared. We could have used any of the other equations because we found charge on the previous problem, but we're given the C and the V, so that's the preferable one, so we don't have to worry about multiplication errors. So here we go, 1/2 CV squared. Here's the capacitance. Here's the 3 volts, and make sure you square it, and you get an energy of 3.7 times 10 to the minus 8 joules. Now let's double the distance of the plates. What would be the value of the charge on each plate now? Well, here's our equation for the capacitance, the physical capacitance, right? It depends on the cross-sectional area, permittivity, and the distance between the plates. So we're going to double the distance. So our new capacitance, which we'll call C prime, is epsilon 0A. They both stay constant, and we've now doubled the distance, so we write 2D. And check out the highlighted part here. Have you seen that before? Epsilon 0A over D? Yes, that's the capacitance. So I just replace that with C, so you now have C prime is equal to C over 2. This time we need to see how the charge changes. So we start with our equation here, and we'll solve that for Q because that's what we're going to be looking for, how that changes. First thing we'll note is since there is no mention of disconnecting the capacitor, assume it stays connected, so the voltage will stay the same. So now we're going to have the capacitance, and our new charge, Q prime, right here, is going to be C over 2, right? We take that C and cut it in half, times V. The highlighted part, CV, is just the original charge here because the voltage stays the same. So the new charge is going to be Q over 2, right? This term, you just replace that with Q, and it's Q over 2. So the charge on each plate halves. Now, how much would the stored energy change? So we use our equation for energy. We just determined on the previous slide that the capacitance would halve if the distance doubled. And again, the voltage would not change because the power supply is not affected by changes in the capacitor. So having the capacitance means that the new energy, and see how we put the prime there again, is going to be 1/2 C over 2, okay, because that's where the capacitance got cut in half, times V squared. The highlighted part there is just UC, right over here. 1/2 CV squared, and if you just look at the yellows, we have 1/2 on this right here. We have 1/2 CV squared times a half. So our new energy is going to be UC over 2, so the stored energy will be cut in half. And just drawn again here, right over here, that's the original energy storage, UC, and then you have that half in front of it.